Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on November 4th, 2025, about 5 days ago. Alright, this paper introduces a portable, motion capture-free teleoperation and data collection system for humanoid robots that can collect 100 demonstrations in 15 minutes with an almost 100% success rate while preserving full whole-body control. The paper is titled TWIST2, Scalable, Portable, and Holistic Humanoid Data Collection System. And as we'll see later, the implications for scaling autonomous humanoid skills are exciting, because low-cost and high-volume demonstrations unlock fast training and real deployment. Okay, Figure 1 presents the system at a glance, summarizing portability, data collection, and learning. The top left panel highlights a portable motion capture-free setup that finishes in about 1 minute. The bottom left panel shows scalable data collection, with about 100 successful pick-and-place demonstrations in 15 to 20 minutes. The top right panel illustrates holistic, whole-body teleoperation for long-horizon, dexterous tasks. The bottom right panel presents Visuomotor policy learning with a hierarchical controller, while the center emphasizes egocentric vision and a 2-do-F neck. So the previous figure summarized the pipeline. Table I now compares humanoid data collection systems across practical criteria. The table lists category and source, then portability, no calibration, single operator, whole body tracking, and holistic control features like egocentric teleoperation, foot control, and wrist control. TWIST2 appears as the only entry that checks every box because it is portable, needs no calibration, supports one operator, and provides full whole body and egocentric control. Alright, Table I set the practical criteria. Figure 2 shows how the system delivers them end to end. The left panel presents the portable setup with PICO4U gear and a low-cost 2-do-F neck that enables egocentric active vision. The middle pipeline illustrates whole-body teleoperation, where a motion retargeter and a general motion tracker translate human motion into high degree of freedom robot joint targets, so data collection scales quickly. The right panel summarizes Visuomotor policy learning, with a diffusion policy predicting future commands that the low-level tracker executes. So the previous figure outlined the pipeline end-to-end. Figure 11 presents closed-loop autonomous executions that the learned Visuomotor policy drives. The top panels depict Kick T, where the robot kicks a T-shaped box and stabilizes with a follow step, showing coordinated leg and balance control. The bottom row shows whole-body dexterous pick-and-place, where the robot bends, grasps a cup, and deposits it. The rightmost panel highlights 6 consecutive successful grasps, which signals reliable fine manipulation. So, the previous figure showed autonomous rollouts. Table 3 reports collection efficiency across users and settings. The complete system reaches about 20 of 23 successful trials to gather 10 demos, with an average time near 68 seconds, which is the fastest stable setup. Removing stereo slows to about 98 seconds, and removing the neck slips to roughly 1-2 seconds with lower success. Using third-person pass-through stays quick at about 69 seconds, but it relies on standing beside the robot, so it is not practical for mobile tasks. Wrapping up, 2 takeaways stand out. A low-cost, motion capture-free teleoperation setup that gathers around 100 high-quality demos in minutes, and a hierarchical Visuomotor policy that turns those demos into autonomous whole-body skills. The implications are big. Cheaper data and scalable training push humanoids closer to real deployment. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.